Hello everyone, this is Dr. Banani Roy. I'm the Assistant Professor at the Computer Science Department of University of Saskatchewan. I'm one of the co-authors of this paper with the title Supporting Readability by Comprehending the Hierarchical Abstraction of a Software System. I did this work with other two co-authors who are Abhijit Bhattacharjee and Dr. Kevin A. Schneider. In short, the main motivation of this work is that developers spend a lot of time to understand source code in order to solve issues caused by other developers. And in case of new developers, they spend a lot of time to understand the source code with the poor or no documentation. If the developers are aided with a tool that can help them to understand the source code effectively and efficiently. Now the question comes, how developers actually comprehend source code. What developers usually do is that they first look the name of the functions of source file to understand the intention of the functions. Therefore, the function names can be utilized for abstracting a system's higher level functionalities. So from the function names, it is possible to abstract the higher level functionalities of the system. And when developers usually takes the higher level representation of the software system, then they go to the lower level representation, which is the source code of the system. That kind of comprehension approach is called top-down model. Whereas in the bottom-up model, developers first understand the source code, then they gradually go to the higher level representation of the source code in order to better understand the software system. Then the last technique is the integrated technique, which actually combines both the top-down and the bottom-up models for program comprehension. In our approach, we have actually followed a bottom-up model for program comprehension. How we can generate a hierarchical abstraction of a software system. So in order to generate the hierarchical abstraction of a software system, first we need the source files, and from the source file we need to generate an abstract syntax tree. From the abstract syntax tree, we need to extract the caller and callee relationship of the functions. Then we generate the static call graph, which basically combines all the execution paths of a software system. And then we extract the execution paths as sets, as different sets. And from the execution paths, which are sequence of function calls, we calculate the similarity matrix. And from the similarity matrix, we calculate the clustering of the execution path, which actually is the hierarchical abstraction tree. And we use the linkage algorithm in Python to develop a dendrogram that shows or builds a hierarchical representation of the source code based on the relationship of the execution paths. And from the hierarchical abstraction tree, we actually label the intermediate nodes and the root node of the tree using a meaningful name, with a meaningful name, using different information retrieval techniques like TF-IDF, and then we obtain the concept cluster tree. So here is the more detailed view of the approach. So here you can see the similarity matrix values, and we calculated the similarity matrix value using Jaccard similarity matrix. And we used the linkage algorithm to obtain the dendrogram, and from the dendrogram we actually obtained the concept cluster tree. And here you can see the color and collie functions, and from the color and collie functions we get the static call graph, and from the static call graph we obtain the list of execution paths. Here we have used Thyan module to obtain the AST from the Python library. Okay. So here we showed a little bit more about the concept cluster tree. So in the concept cluster tree, the leaf nodes like 4, 5, 6, and 7 are mapped with the sequence of function calls, which are execution path. And then using the Jaccard similarity matrix, the leaf nodes are combined into some intermediate nodes until a single node is obtained. Okay, and naming these intermediate nodes by analyzing the execution paths that belong to them might reduce the need to go through in detail about their functionality. Okay, that's the main objective of this work. Renaming the, labeling the intermediate nodes with a meaningful name using different information retrieval techniques. So here is the algorithm for obtaining the CC team. So first we obtained the entry node and exit node. From the entry node and exit nodes, we calculated the execution paths, and from the execution paths, we calculate the Jaccard similarity matrix, which is their distance matrix. And then we created the cluster tree with node labels, and after that we actually created the concept cluster tree by applying the automatic labeling. So these are the information retrieval techniques we have used to label the intermediate nodes and the root node. The first one is TF-IDF, frequency inverse document frequency, which is an information retrieval technique. In this technique determines a score of terms using frequency and inverse frequency of terms in a corpus of documents. We used a scikit-learn library for implementing the TF-IDF technique. And the LDA and LSA are the topic modeling techniques, and these techniques actually map the terms with topics. And we used GenSim library to implement these two topic modeling techniques. Different related works exist to obtain names for hierarchical abstracted tree node. One of them is proposed by Garib et al. But the main drawback of this approach is that they only considered one information retrieval technique, and they actually didn't do any user study to evaluate the automatic naming of the node, like how users actually understand the name in comparison with the manual labeling of the node. In our approach, we actually overcome this drawback. And the existing work also considered only function names as the terms, whereas we also considered words in the function name to see the performance of the labeling technique. In our approach, we have investigated 4 research questions using a user study. And in our user study, we have used 3 Python source code, which are open source code. And these projects follow the standard conventions of software developments and follow proper function naming convention, which are very important for the success of the approach. We involved 5 developers in the user study, where 2 are male and 3 are female. They have at least BSc in computer science. We asked the user to rate the automatic summaries of our 3 techniques, each with 2 variations. Additionally, we also provided text box for the participants to input 5 keywords from the description produced by manual analysis of execution paths. And we actually provided a tool UI for the user study, where developers can see the concept cluster tree. They can browse different nodes, and they can also zoom the name of the nodes. And we also give them a form so that they can rate the output of the automatic labeling approaches, and they can also provide their suggested keywords for the labeling of the node. So in our first research question, which is about how well does the automatic labeling perform using the candidate approaches in comparison to manual labeling, we actually make use of the pyramid score, which is used in natural text summarization tasks to compare an automatic summary with a manual summary. Here, greater pyramid score means that the automatic naming matches more with developers' suggested names in our case. Okay. So our result shows that TF-IDF word variation got an average of 64% overlap. So developers input matched mostly with the TF-IDF word variant technique. Then to answer the research question 2, which is how do developers evaluate different labeling approaches based on function names, we asked the participant to rate each technique summary with a score ranging from 1 to 5. And the result shows that users preferred LSI naming technique than LDA. Also, like the TF-IDF and LSI technique showed the similar kinds of performance. In our third research question, how do developers evaluate different labeling approaches based on words in method names? So in this research question, we can see that among our 12 cluster nodes, in 7 of them, developers preferred names suggested by TF-IDF and LSI technique than LDA technique. Therefore, research question 3 can be answered to establish that words in function names variation perform better with TF-IDF and LSI than LDA. So our fourth research question is, how can we compare the preference of developers between the 2 approaches addressed in research question 2 and research question 3? So our result shows that word variant techniques got a minimum of 5% more rating compared to method variant technique. In summary, in this paper, we adopted 2 topic modeling techniques to name nodes along with the TF-IDF technique. We introduced the uses of words in the function name as term. We conducted a small scale user study to evaluate the proposed techniques. We found that TF-IDF generates natural label compared to other techniques. Using words in function name as terms performs better than using function name as terms. And the previous studies actually didn't consider the words as terms during the labeling process. In future, we want to leverage patterns in execution paths. We want to generate a natural text summary using method comments to give more description for the node names. We want to use code comment generation techniques for that. We want to develop an interactive tool to browse a code repository. And we want to support more languages like Java for generating concept cluster. Thank you.